Exponential functions are used a lot to model real-world situations, and we have two different types. We have exponential growth, where something is growing and shooting up like that rocket ship that we saw in our initial exponential lesson. We also can have exponential decay, where it's getting smaller and smaller and smaller as it gets closer and closer to zero. Now, we have two different formulas for growth and decay, but they are almost identical. Let's take a look at exponential growth first. We have f of t equals a. Now this a value is going to be our initial or beginning value. So whatever number we start with, that's going to be in the place of a. Then it's times 1 plus r, and r is our rate, where we will use our percentage, raised to the t. Now, these are exponential functions, so they do have a variable that is the exponent, and t stands for time, often in years. Now, the only difference with exponential decay is instead of 1 plus, decay is 1 minus that rate. You still have your initial value for a. We still have our rate will be used as r, and t will represent time. So they're almost identical formulas. We are just going to add 1 with our growth, and we will subtract 1 away from our rate when we're working with a decay. Let's look at our first examples. It says, given the following exponential function, identify whether it represents growth or decay, and determine the percentage rate of increase or decrease. For number 1, you've got y equals 65, that's your a or your initial value, times 1.25 raised to the x. Now, is this growth or decay? This is a growth exponential function. I know because inside those parentheses, there was 1 plus 0.25, or 1 plus 25% was added here. So that takes us to, what was that percentage rate? That percentage rate was 25%. It is growing by 25% over time. Let's look at number 2. Y equals 38 times 1.108 raised to the x, growth or decay. This is another growth. I know because we had 1 added to 0.108, which means 1 was added to, can you tell? Your percentage there was 10.8%. Changing our decimals to percentages, you shift your decimal 2 places. Our growth was by 10.8%. Number 3, y equals 42 times 0.92 raised to the x. Can you tell this time? Here's our rate, 0.92. This is a decay. Now, it's not decaying by 92%. We have taken 1 and we have subtracted away the rate to give us 0.92. So let's take 1 and subtract 0.92 to determine our rate. 1 minus 0.92 is 0.08, or 8%. So this function is decaying by 8%. Now, you might be feeling a little confused at this point. When we're talking about exponential growth and decay, our rate is always in terms of growth. So even though number 3 is a decay, the value that we use in the function is in terms of growth. It is only growing 92% each time. It's not even maintaining the initial value, the whole percent. It's actually losing 8% each time. So we'll talk about that more as we look at our examples below. Number 4, y equals 8,200 times 0.96 raised to the x. This is another decay. I know because in my parentheses, 1 minus my rate has given me 0.96. So let's take 1 and subtract with 0.96 to determine that rate. 1 minus 0.96 will give us 0.04, or changing that to a percent, 4%. So again, number 4 is a decay exponential function. That rate in the function is always written in terms of growth. It's only growing 96%. It's not even growing 100% each time to maintain what it had before. It's only growing by 96% each time or decaying by 4% each time. So let's see how this applies to real world situations. Number 5, a new car is purchased at $16,400. The value of the car depreciates, important term here, depreciates at 8.25% per year. What will be the value of the car to the nearest cent after 10 years? So depreciates. Does that mean this is a growth or a decay? If you don't know the word depreciates, go ahead and learn that one. That means this is a decay problem. Depreciates means that it is losing value over time. So in our boxes here, we've got a place where we can write that this is a decay problem. We've also got our next box is initial amount. The initial amount or value of that car was $16,400. The percent rate, go ahead and put 8.25%. We'll use that box for our percentage. But now let's determine that growth or decay factor. So I'm going to do 1 minus my rate, 8.25%. But let me change it to a decimal. 1 minus 0.0825 gives me a decay factor of 0.9175. So we have all of our pieces now. We have our initial amount, we have our growth or decay factor, and then we are going to raise it to our time 10 years here in a moment. Let's write our function f of t equals initial amount, 16,400. We already did the 1 minus the rate. We're ready to plug in now 0.9175 raised to the time. They asked us about 10 years. So my exponent is 10. So let's grab the calculator and simplify our function. I'm going to go to New Document, Add Calculator. Let's do 16,400 times 0.9175. You have a caret button here to raise it to the 10th and enter. We have $6,932.73. So here was our decimal form. We are rounding it to the nearest cent. So something else I want to make sure you know, when you have a question that's asking rounding to the nearest cent, that is the hundredths place. That is 2 decimal places. So 7.3 is in the hundredths place. That would be to the nearest cent. So I look at the 4 to tell me how to round. Our car is worth $6,932.73. Number 6, $2,200 is placed in an account with an annual interest rate of 7.25%. How much will be in the account after 29 years, rounded to the nearest cent again? So is this growth or decay? They don't explicitly say, but if you are placing money in an account with an interest rate, it better be growing. So this is a growth. Our initial amount, $2,200. With a percentage rate of 7.25%. Now this is growth, so I'm going to do 1 plus the 7.25%, but change it to a decimal. 1 plus 0.0725 gives us a growth factor of 1.0725. Now this is growing, so every time we are maintaining our initial amount 100%. That's why we add 1 with our rate. We don't want to just grow it 7%, because if you type that in the calculator, it'll actually diminish your value. So we want 1 and our 7%. So our money can grow in our account. F of t equals our initial amount, $2,200, times 1.0725 raised to the 29 years. Let's grab the calculator and see what we get. $2,200 times 1.0725 raised to the 29 is 16,747, and we've got 0.284797. So again, we were asked to round to the nearest cent. That's hundredths place on this problem. We've got 2 8 is in the hundredths place, so again, we're looking at 4 to give us $16,747, and let it rest 28 cents. Number 7, an element with mass 590 grams decays by 19.5% per minute. How much of the element is remaining after 15 minutes to the nearest tenth of a gram? This is clearly a decay. They even use the word decays. Our initial amount, 590 grams. It's decaying by 19.5%. Now this is decay, so we're going to do 1 minus the 19.5%, or 1 minus 0.195, gives us 0.805. Let's write our function. F of t equals the initial amount, 590. We've already computed our decay factor as 0.805, raised to the time. Now, I mentioned earlier in our notes, our variable, our exponent of t is usually in years, and this problem is in minutes. Don't let that bother you. They have given us everything in terms of minutes. They're asking about minutes. They gave us a rate in minutes. So just for this problem, our t does represent minutes. So raised to the 15. Let's grab the calculator and see what we get. 590 times 0.805 raised to the 15th. 22 and 79240835. So this time we were asked to the 10th of a gram. 10th is 1 decimal place. I know they wrote it as 10th, tenths place, but 1 decimal place. So at the 7, the 9 tells me how to round. That tells me we have 22.8 grams. And number 8, a town has a population of 13,000 and grows at 4.5% every year. What will be the population after 13 years to the nearest whole number? This is a growth. Our initial amount, 13,000 people. 4.5% is our rate. It is growing, so do 1 plus 4.5%, or change that to a decimal. 1 plus 0.045 gives us our growth factor of 1.045. Writing our function f of t equals initial amount 13,000 times our factor 1.045. We want to know after 13 years, and we'll round to the nearest whole number. 13,000 times 1.045 raised to the 13 years. 23,038.5492642. So we're rounding to the nearest whole number. That's going to be the 8. The 5 tells us how to round. So we have 23,039 people. So there's exponential growth and decay. Exponential growth, it's going to grow so quickly because we are raising our time as our exponent and we are multiplying each time. Exponential decay is going to get smaller and smaller. So as you work through your word problems, be sure you identify whether it is growth or decay, because that'll help you determine whether you need to be adding 1 to your rate or subtracting 1 from your rate to give you that growth or decay factor. Evaluate and be sure you are rounding correctly as you work through those problems. Let me know if you have any questions, guys, and I'll see you in class.